Since the discovery of graphene, there has been increasing research into dimensional materials because they have fascinating properties that are especially interesting for electronics and new devices. In particular, we need semiconducting materials for applications in low-power transistors, in detectors and sensors. In our study, we used molybdenum disulfide, or MoS2, because it's stable, it's easily available, and it has a relatively low bandgap. The first challenge with 2D materials is always obtaining large flakes. To do it, we exfoliated on gold, which acts as a tape because it forms a strong bond to the sulfur atoms of MoS2. In this way, we can get monolayer flakes of various millimeters in size, up to a centimeter. We then wanted to inspect our samples by scanning tunneling microscopy, so we could image them with atomic resolution and get insights in their electronic properties. This was challenging because samples for these measurements are usually prepared in ultra-high vacuum, so that they are really clean. But surprisingly, with our samples, it was not that difficult, as it was enough to place them in vacuum and heat them to 400 Kelvin to obtain clean surfaces and get high-resolution scans. When inspecting the samples in STM, we came across small protrusions. These are nanobubbles that naturally form because of contaminants trapped between MoS2 and the gold surface. Previous studies showed that their aspect ratio, the ratio between their height and the radius, is a constant independent of their size, and so is the strain. However, our nanobubbles are much smaller than those observed previously, and we found out that the aspect ratio was actually decreasing, going towards the lowest sizes. As it was reproducible, it seemed to reflect a fundamental law, and therefore it caught our interest.
So, to support the experimental measurements performed by tunneling microscopy, we decided to incorporate in this study computational results. To this end, we assessed the formation of MoS2 bubbles using atomistic simulations, which gave us atom-level insight into this process. We employed classical molecular dynamics, or MD simulations. The main advantage of this method is that one can visualize the dynamic evolution of systems made of millions of atoms. The simulations consisted of monolayer MoS2, a flat gold substrate, and trapped matter between the membrane and the substrate. This MD system is relaxed over 1 nanosecond, which actually allowed us to have computational bubble relax at room temperature. We ran several simulations that created MoS2 MD nanobubbles of different sizes, and by analyzing this output data, we have all the fundamental information to study the topography and the strains of these MD bubbles, and then compare these computational results with the experimental data. Not only did the simulations corroborate the scaling breakdown of the aspect ratio found in the experimental nanobubbles below a critical size, but also the simulations indicated that the strain in MoS2 bubbles varied as well in this subcritical size regime. This outcome is extremely interesting because it is known that a change in strain changes the bandgap in MoS2. So in the bubble formation process, we found a route to tune the bandgap in monolayer MoS2. Moreover, the strains obtained from the simulations indicated that bubble formation in MoS2 leads to the generation of donut-like shapes in strain, where the maximum is located close to the periphery of the bubble and the minimum is located at the center of the bubble.
Finally, we used the spectroscopic capabilities of STM to measure the bandgap of our nanobubbles. By doing this on bubbles of different sizes, we could verify if strain and bandgap tuning indeed correspond. The results were promising, as we could see the bandgap changing by 400 millielectronvolts in bubbles in the subcritical range. This is very interesting, as it means that we can tune the bandgap by changing the size of the bubbles. For instance, if we can introduce Taylor molecules between MoS2 and gold.
It turns out that the strain of the bandgap of MoS2 bubbles, which are natural photon emitters, can be tuned by controlling their size. This can be used in optoelectronic devices to fabricate tunable emitters. Even we could observe single photon emission.
Additionally, though we used only MoS2, this tunability derives from the elastic properties of 2D membranes. So, we expect our results to apply to other 2D materials with different electronic properties.